We now look at Gauss's law, for which the first thing we need to see is what we mean by electric flux. This is written as a phi, and the units are newtons per coulomb and a meter square. Now, the flux is how much of something passes through a unit area or a given area. So let's suppose that we have a parallel electric field. So that's our electric field, which is uniform. So the spacing between the lines should be the same, and all of them are parallel to each other. So it's a uniform electric field. And let's suppose we have an area which is, well, we'll show it like this. It's a rectangular area that's perpendicular to the field, and the area is A, and the strength of the electric field is E. Now, if we say that a given electric field corresponds to a certain number of lines of electric field, then the stronger the electric field, the more lines there are. So if there's a certain electric field that has a certain number of lines, then how many lines will pass through an area A? And that will be given by E times A. So if, for example, for an electric field equals, say, 100 newtons per coulomb, we say that it's represented by, let's say, 50 lines every square meter, and this area A is, let's say, it's 2 square meters. So how many lines will pass through this area? So if there'll be 50 lines per square meter, that represents 100 newtons, and so we will have a total of 50 times 2, which is 100 lines will be passing through 2 square meters, and that would be the flux of, or the number of lines. That would be the electric flux. So the electric flux is written as E times A. Now this is if the area is perpendicular. But what if the area is not perpendicular and it's tilted? So for example, it's an area that seen from the side, it's like this. Then the number of lines would depend on what is the projected area, or this area, the area that's perpendicular to the lines. So this area is A, and the projected area, if this angle is theta, the projected area, we can write it as A perpendicular, that is going to be A cosine of theta. And therefore the electric flux in this case through this area is going to be E times A perpendicular, or E A cos theta. Now the electric field is a vector and the area is a vector, and the direction of the area is perpendicular to the area. This is the direction of the area, and we can write the area as pointing in this direction, and that's the unit vector, and that's the vector area. And then this is the electric field, and that's the A. So this is the angle theta, which is the same as this angle, and therefore we can say that we have the flux is an electric field E and an area A and cos theta. So EA cos theta is simply E dot A. So the flux is a dot product of E and A, and that is our definition that we will use, E dot A. Now if we have, for example, an area that's not simply flat like this, but we have lines of force that are going, again we'll deal with a uniform electric field for the moment, and then we'll see what would happen if the field is not uniform. And then our area is composed of some flat parts, some smaller parts, some bigger parts. So this is A1 pointing this way, and this is A2 pointing this way, and A3, and well, that's pointing this way, A4. Then this is our theta 1, and theta 2 is 0. This would be our theta 2, and this would be theta 3. And then our flux would be E1, or E, which is constant, times dot A1 E dot A2, and so on, or it would simply be the sum of E dot A, EI dot AI, if the areas are different. And this also includes the case where the electric field may be different at different places. If it's the same everywhere, we can take it outside. Now let's come to a slightly more complicated case where we have a surface that's more or less a closed surface. So let's suppose we have a region of space that is like a balloon, for example, and we have a, let's still assume a uniform, or let's have a non-uniform electric field. So we have a charge here that has an electric field going outwards in all directions. And the question is, what is the flux of electric lines through this area? So we'll have a line of force, that line of force of electric field that's going like this, and assuming that there's no absorption and no creation of electric field inside, whatever electric field line enters this bubble will have to leave it. And there's another line that enters here, and that will leave from here. So a line enters this little dA, that's our little area, and that's another area, and we'll have an area here and an area here. And we have an electric field that's entering here and one that's leaving here, which would mean that the flux, which is the sum of every EI dot AI, where this would be, for example, E1, this could be E2 or E3, E4, and there will be a lot more like that, and then this would be A1, A2, A3, and A4. And well, we would have little areas over the entire surface. So since any flux line entering would be also leaving, therefore the net flux, which would be equal to the flux that's leaving minus the flux that's entering, and that would be equal to 0, because whatever enters has to leave. And so we can say that if the charge is here, not inside, it's out here, then the net flux due to that charge will be 0. Now we can try to prove this again by a little bit of calculus, not bit calculus really, but just analysis. So let's suppose that we have a x, y, and z coordinate system, and we have a cubical volume instead of a spherical or oval shaped volume. We have a cubical volume, so that's going to be like this. And let's also assume that we have a flux, an electric field that's pointing straight in the positive x direction. So we have an electric field coming from here. Uniform electric field from the left going towards the right. Now we'll call this area the one that's behind this one as A1, and that area is going to be pointing this way, and this area is A2 that's pointing this way, and then we have this top surface, this area pointing this way, that's A3, the bottom area pointing downwards, that's A4, and then one on the this face being A5, and the one that's behind it as A6. Then the flux through this closed surface is going to be equal to the sum of the E dot AI. So it's going to be E dot A1, E dot A2, E dot A3, 4, 5, and 6. And E is the same for all cases because it's a uniform field. Then for A1, it's going to be E A1, and the direction in this case, the theta is going to be, well, E is like this and A1 is like this. So the angle is 180 degrees. And then we do E times A2, and E is to the right and A2 is also to the right. So they are parallel, so it's cosine of 0. And then we take the other one, E of A3. So the E is like this and A3 is perpendicular, angle is 90 degrees. And we can see that it's going to be 90 degrees for A4, A5, and A6. A4, A5, and A6 would all have cosine of 90 degrees. Now, cosine 90 is 0, so all of these would add up to 0. And cosine 180 is minus 1, and cosine of 0 is plus 1. So it's going to be E A1 minus 1 plus E A2 1. And since the areas are equal, therefore this is going to be equal to 0. And so the net flux in this case is 0, which simply means that what's coming in is going out. Now, what happens if the source is inside this volume? So instead of the source or the source of the electric field being outside, which has to be coming from some charge, if there's a charge inside it, then what would happen? So let's consider a spherical surface. So we have a solid, a spherical surface. This is just a imaginary surface in space, and we have a charge Q which we put right in the middle of that surface, and we want to find the net flux that is leaving this surface. So we have our equation, flux equals E dot dA, E dot delta, E dot A, and sum of all of these. So we can modify the equation for this case because we don't have a in the case of this cube, it was easy to have straight edges, but here we need to say that, well, in the limit when delta A tends to 0, then the summation of E dot delta A will become the integral of E dot dA over the entire surface, and that will be the flux. That is our equation that we will use. Now we can, in order to try to solve this integral, we can take a little element of area here. That's a little piece of area on this surface. That is our delta A. And the direction of delta A is going to be, that's the direction of delta A. And the electric field here is going to be E. Now, we would write the flux as integral of E dot dA, which will be an E dA and cosine of an angle. And we see that at every point along this surface, the area, the direction of the area is parallel to the direction of the electric field, or area at every point is parallel to the electric field. And because it's the same everywhere, this angle is going to be 0 degrees. And well, cosine theta is cosine 0 is 1, so it's constant, it can be taken out. So now it's just 1, so we can also ignore it. Now the electric field at this point is given by K Q over R square, where R is the radius of this sphere. Well, that's the magnitude of this field. The direction would be E vector would be K Q over R square unit vector R, and the unit vector R is pointing straight out. But we've already accounted for that unit vector in the cosine theta being 0. So now we know that E is constant everywhere on that surface. Okay, it's the same everywhere because R is the same everywhere. K is constant and Q is just one charge. Yeah, this is not constant everywhere because the direction is changing, but the magnitude is constant. And now we have the magnitude because we've accounted for the angle. Because E is constant everywhere, we can take it outside. And therefore our flux would become, we'll take the E outside and we'll have an integral of dA, and cosine is simply 1, and integrate over the entire surface. And when we do the integration, the surface is simply the area of the surface of the sphere, which is 4 pi r square. And therefore we can write the E from here. So our flux is going to be K Q over R square, that's the E, times 4 pi R square. And the R square will cancel with the R square. And we have 4 pi K Q. Now, that makes it a simple equation, but we know that 4 pi K is written as 1 over epsilon naught, where epsilon naught is the permittivity of free space or a vacuum. And so we can replace that with 1 over epsilon naught, and the flux becomes Q over epsilon naught. So the flux over this entire surface is equal to the charge that's right in the middle divided by the permittivity of free space. Now, to make sure that this charge is inside, because we found earlier that if the charge is outside, the flux is 0, we can add a little in over here to say that the charge is inside this spherical surface. So this is the case where the charge is right in the middle. But what would happen if the charge were not in the middle and it was off center. In that case, R, the direction of the electric field, and A, the direction of the little area here, would not be parallel, and so we would not be able to have a cosine 0 everywhere. It'll be 0 at just 2 points, but it won't be 0 everywhere. So if the charge is not right in the middle, then what happens? So let's suppose we have a charge right here, and we have a surface that's not symmetric around it. So let's say here's our surface, let's take it, that's a charge, and that's our surface, which is no longer concentric, the charge is no longer in the middle. So in order to solve that, we'll just make another Gaussian surface, which is, or another volume, for which charge is right in the middle. And we'll see what is the flux over here. And the flux here is Q in over epsilon naught, which is what we have here. So that's the flux that's leaving this surface. And as it leaves this surface, it has to leave this surface. Any flux leaving this surface has to ultimately leave the other surface. And therefore the flux to the outer surface is also Q in over epsilon naught. So it doesn't matter if the charge is in the middle or if it's off center. Now what happens if the surface is not spherical? Well, let's make a non-spherical surface, but it has to be a completely closed surface. In that case, whatever flux is leaving here will ultimately leave from here. So the flux that leaving this surface is Q in over epsilon naught. The flux that leaving the irregular surface is also Q in over epsilon naught. And so we have this relationship that the flux is Q inside over epsilon naught for a closed surface. And that is Gauss's law, that the charge inside a closed surface will create a flux given by this value.